Well, should we start?
Sorry, I'm just muted. Yeah, I think maybe we can get started. And we do have some students, I don't know, some technical issues for joining us. So we just ask them to watch the YouTube live channels. All right, everyone. So welcome to our second Sensor Week for 2022 seminar series. So my name is Yishan, and I will be the moderator for today's webinar. So for those who just joined us for the first time, I just want to introduce our Census Rig a little bit. So the Census Rig is a multidisciplinary group of researchers with interests like sensor materials, methods, devices, and with various applications. So our group provides an opportunity to exchange ideas, present early findings, and explore collaborations and funding opportunities. So our goal is to connect sensor technologies and establish a connection between academia and industry. So today, it's my great pleasure to introduce our today's speaker, Dr. Richard Kirkholm. Dr. Kirkholm received his bachelor's and master's from Oxford University and PhD from University of Southampton in UK. His thesis involved classical infrared and Raman studies of small inorganic molecules, including matrix isolation and isotopic substitution. So Dr. Kirkholm is now the principal at Kirkholm Spectroscopy Consulting. He works with both emerging and established instrument companies, as well as users of these instruments, or miniatures, optical technologies, and etc. So he's the former president of the Society for Applied Spectroscopy, and he has led the effort to establish a second scientific journal, which named Applied Spectroscopy Practica, which I believe will launch in next year. And he also published extensively on the technologies and applications for miniature and portable spectrometers. So with that, Dr. Kirkholm, the floor is yours.
Okay. Thank you for the introduction, and thank you for the invitation to give this talk on portable spectroscopy. Okay, so you may think that all spectrometers are these 2-foot square beige boxes that sit in the lab, need to be treated with extreme care, and who produce data spectra that needs a graduate student, a PhD, or a professor to interpret. But that's not the case today. There are a large number of spectrometers that are effectively used in the field by non-scientists. And as the technology continues to shrink and shrink, we're going to see spectroscopic sensors in household goods and wearable devices. So this talk is in two parts. So the first half looks at commercial portable spectrometers available today and their applications. And then the second half looks ahead to miniature spectroscopic sensors and how they can be incorporated into consumer goods and what lies ahead. So over the last 20 years, a combination of advances in consumer electronics, telecommunications, optics, photonics, etc., has driven the development of a wide variety of portable spectrometers. And the applications of these are very diverse, from safety and security to all types of recycling to field geology, and they've got particular importance in the pharmaceutical industry. So I'm regarding a portable spectrometer as an analytical instrument that generates clear answers for its operator when it's carried to the sample. In other words, we're taking the spectrometer to the sample rather than sample to the spectrometer. For an optical spectrometer and some of the other techniques as well, ideally it should operate in what people call point and shoot mode, or at least minimize sample handling. And the primary result from the instrument is not a spectrum, but it's a result. It's an answer to a question. In some cases, that result might be sample identification. In other words, it might be some kind of pass-fail message. In some cases, it might just be an audible alarm with a red light or a green light. The operators of these instruments in the field are rarely scientists, but they may be people like hazardous material technicians, armed services personnel, and even scrap metal dealers. Although they're portable instruments used in the field, they may have to conform to regulatory standards. And there's one called 21 CFR Part 11 in the pharmaceutical industry that governs electronic records and signatures. And if an instrument is being used by law enforcement, by the police, by customs, border, it may have to conform to legal standards for the admissibility of evidence. So there can be quite sophisticated software inside these instruments. You also have to be aware that they may be used in potential life-threatening circumstances. This could be in the military when dealing with something that could be an improvised explosive device. It could be the police or first responders looking at some suspicious white powder. It could be a hazmat technician looking at a chemical spill. So there are many instances where, as I say, these are used in quite critical circumstances. So what has enabled spectrometers to be shrunk to portable size? For all of them, it's really based on the continuing revolution in mobile computing power and processors, memory, the development of very nice user interfaces, communications technology like Wi-Fi and Bluetooth that go in small devices, MEMS and MOEMS devices in some cases. And for any portable device, everything that people have learned about increasing battery power and managing power on a portable device very well. And then fairly critically, in order to produce a result, there's chemometrics and choice of algorithms that have been developed over the years. And what we're now seeing is what people call the cloud. In other words, the ability to upload data to the cloud, do some processing there, and download information. So that really applies to all portables. One's operating in the optical region of the spectrum. Optical telecom has been a huge driver here in miniaturization, things like diode lasers, fiber optics, cameras, sensors, array detectors, compact spectrographs. Specifically for Raman, very fast cutoff optical filters are critically important for these small devices. And for infrared, ATR, that's attenuated total reflection technology, often using diamonds, has been key. Small XRF, X-ray fluorescence instruments have their own enabling technologies, miniature X-ray sources, rapid developments in X-ray detectors, especially something called a silicon drift detector, miniaturization of pulse counting electronics, and then the algorithms there, something called fundamental parameter theory, that's used to convert an XRF spectrum into quantitative results. In mass spec and the combination of gas chromatography and mass spectrometry, it's the development of miniature ion traps that are really the key technology. And then associated with them are miniature pumps, so pump technology. In GCMS, narrow bore GC columns. In general, mass spec sampling and sample introduction and ionization methods. There have been developments in all of those over the past 20 years that have enabled portable mass spec and GCMS. The driver for this is really the generation of a lot of value. So if you take the spectrometer to the sample, you get instant actionable data. In other words, you get a result and it tells you what to do next. So you get answers at the point of need where the sample is. That, for instance, could increase safety. In the case of incoming raw material for a chemical or pharmaceutical process, it's reduced cycle and waiting time. And in general, by doing this, as opposed to sending samples off to the lab, you increase efficiency, you increase quality, and you increase process confidence. So it really is transformative, the ability to take a spectrometer to the sample instead of vice versa. This is a list of ideal and possible features of portable spectrometers, and current commercial devices do incorporate many of these. So in terms of sampling, as we've indicated, no physical contact between the instrument and the sample is very valuable. What's called an optics free space coupling, which mean that you don't have to handle a sample. You don't have to prepare a sample. You don't have to use a sample cell, cuvette, or reagents or anything like that. And ideally, in being able to interrogate the sample through an optically transparent container. You can't do that for all techniques, but some of the optical techniques you can, and that's very important. On the logistics front, I mentioned 21 CFR Part 11, which if you use a scientific instrument, a spectrometer, in pharmaceutical manufacturing, you really have to adhere to this standard for data management. If you're a large international company and you're deploying instruments around the world, you need fleet management capability. In other words, you need to be sure that every instrument, no matter where it is using the same version of the operating system, same version of the software, the same libraries, the same algorithms, et cetera, et cetera. Often you might want a barcode reader incorporated in your spectrometer. So if you're, say, checking incoming raw material, you can read the barcode that tells you what the material should be or purports to be, and then you can run the spectrum to confirm that. In any manufacturing area, you need to be able to upload data to a quality system. And obviously, it's really nice if the battery and power consumption are such that you can run for a whole shift without swapping batteries or having to recharge. In other words, an 8-hour operating time. In terms of the environment, you're using these instruments in the field, so you need to be able to operate over a wide variety of environmental conditions. And I'll talk a little bit more about this later on. For a handheld instrument, you want it to be lightweight. Obviously, you don't want to carry around something heavy. And lightweight, it tends to mean under 2 pounds or under a kilo, and the lighter the better. In many cases, these will be operated by people wearing some kind of protective equipment, at a minimum sort of lab gloves, but it could go all the way up to sort of heavy duty hazmat suits or bomb disposal equipment. And so that means you've got to pay attention to how you control the instrument, the size of the buttons, are you using a touch screen, etc. How visible is the touch screen, etc. You're using these in the field, so they need to be at least dust and splash resistant and drop and shock resistant. A portable instrument used in the field will get dropped. In terms of results, if you're using this to identify things, the answers need to be unambiguous because you're giving that information to a non-scientist. It needs to be unambiguous even if you've got a mixture. So you need algorithms that can disentangle mixtures and tell you what the constituents are. If you're doing identification, you'll need some kind of built-in spectral library. If you're doing quantitative analysis, you'll need a calibration. It's very useful to have ancillary data available, and this is especially important in something like hazardous materials. If you think about it, let's say a truck rolls over and liquid spills out. A hazmat technician goes in there with a spectrometer and it says it's acetone. That may not mean much to him. He's not a chemist. What he needs to know is it inflammable? Is it volatile? Is it explosive? How to handle it? Can he just hose it down? Or if he hoses it down, is it going to poison everything in a river? So having ancillary data available is very useful in certain circumstances. in some cases, all an operator needs is a red screen, green screen. That yes, this is the right material. No, it's not the right material. This is benign material. This is hazardous material. And then additional features, the ability to communicate with other devices, Bluetooth, Wi-Fi, in some case cellular communications are very valuable. And then documentation of the sample can be critically important in a number of areas. So a micro and a macro camera, GPS, so that you know exactly where that spectrum was taken, and time and date stamps. And many of these properties are in fact built into commercial spectrometers today. So a little bit on background and history. A lot of the developments in portable instruments have somewhat unfortunately been driven by terrorist type incidents. So back in the early 1980s, an Air India flight was bombed and brought down over Canada. And the Canadian government then looked at what means are there to, if you like, sniff out explosives potentially being carried onto aircraft. And they funded developments in a technique called ion mobility spectrometry, developing these handheld instruments that are very sensitive and sniff things out. Developments in handheld X-ray fluorescence were more driven by commercial drivers, and those instruments started to appear in about 1994. The first portable GC mass spec, which is about the size of a briefcase or attaché case, appeared in about 1996. First portable FTR in about 2001, right about the time of 9/11, and a lot of them were sold after 9/11 to identify suspicious materials. Following on soon after that, the first really complete portable Raman instrument designed for a specific purpose was introduced by a company called Ahura. That was closely followed by the first portable near-infrared instruments. Laser LIBS, which is laser-induced breakdown spectroscopy, came along a fair bit later in portable formats, been available in the lab for a long time. So the first handheld portable LIBS instruments in 2013. In 2014, an instrument called a high pressure mass spec was developed that we'll talk about a little bit later. That's a handheld mass spectrometer. And then as you shrink all of these devices, that opens up the possibility of combining them and having two spectroscopic devices in one box. And Thermo Fisher Scientific did that with a product they call Gemini, which is combined FTIR and Raman instrument, introduced in 2015. So what do these instruments look like? So just going through these. So in the top left A, that's a portable GC mass spec, gas chromatograph mass spectrometer. This one's made by PerkinElmer, and it's also distributed by Smiths Detection for safety and security applications. And it's a size and weighs about 30 pounds. C and D are both handheld X-ray fluorescence instruments, and I call this the cordless drill form factor. And so these work by emitting an X-ray beam from the snout of the instrument and picking up X-ray fluorescence and discriminating them by wavelength, and by using that you can do elemental analysis. These are open beam X-ray devices, so you're limited as to the amount of power that you can put out, the amount of X-ray power you can put out. In some circumstances, like field geology, it's useful to be able to put out more power. And the little box in the top right is a field XRF with a more powerful X-ray source, but it's got a lid which incorporates shielding, so it's no longer an open beam device, but it's rugged and it can be taken out into the field. The bottom three instruments are all portable Raman instruments. These tend to be, this rectangular form factor. They could be almost the size of a paperback book, and the most recent ones are actually the size of a deck of cards. So these are common form factors, with what I call the cordless drill form factor and the rectangular form factor probably accounting for most of the instruments. So again, because they're intended for use in the field, they have to perform well outside a climate-controlled environment. So they have to operate and maintain their calibration over wide ranges of temperature and humidity, have to be dust and water resistant, if not waterproof, and capable of withstanding physical shocks. Some of them absolutely have to be waterproof. If they're used for detection and identification of hazardous materials, they have to be able to withstand a decontamination procedure. And commonly that involves getting a bucket with dilute bleach solution and a toilet bowl brush and scrubbing the instrument down. And if you think about doing that to a lab instrument, you'd be greeted with complete gasps of horror if you tried to do that. But literally that's what's done to some of the instruments that need to be decontaminated. So instruments can get rained on in the field. Instruments used for field geology can be used in very cold climates, very hot climates, obviously dusty climates, and so they have to withstand that. The bottom two instruments here are really designed for safety and security in the military. One of them is a Raman instrument and one of them is an FTIR instrument. And you can see they've got these big rubber bumpers on them. And that's to protect them, if and when they do get dropped. And as I say, any portable instrument will get dropped. And there's actually a military specification that says how the sort of tests an instrument has to go through to prove that they can withstand those kinds of drops. So in terms of spectrometer techniques, we can divide them into optical, which are molecular analysis type techniques, UV visible, near-infrared, mid-infrared, Raman, and variants of mass spectrometry, the high pressure mass spec that I talked about, GC mass spec, and ion mobility spectrometry. Elemental analysis, X-ray fluorescence, and laser-induced breakdown spectroscopy. And then a relatively newcomer for field use and being ruggedized is NMR, nuclear magnetic resonance. And there are examples of that both in the traditional chemical shift type measurements and also in time domain measurements that are sometimes called relaxometry. Now, each technique or instrument has its own benefits, its own limitations, samples it can analyze, samples it can't analyze. So we have to make sure we're choosing the right technique for the problem at hand. So looking at optical molecular instruments, these are widely used for rapid identification or confirmation of chemical substances, often white powders, but also onto fabrics and other types of materials. So these can be used for incoming material confirmation of pharmaceutical manufacturing, detection of counterfeit pharmaceuticals in the field, and identification of any suspicious material by police, customs, border, airport security. And in principle, you can use near-infrared, mid-infrared, and Raman in all of these areas, but each technique has its strengths and weaknesses. Very briefly, Raman spectroscopy is often preferred because of its point and shoot ability. You literally have to handle the sample to use a portable FTIR, and the picture in the middle is a portable FTIR. The little circle at the top is where the sample needs to be placed. Near-infrared spectroscopy has been used for many years for quantitative analysis of natural products like grains and fruits, and it tends to be well suited to those highly heterogeneous materials. If you're interested in detection of counterfeit pharmaceuticals, there's a video you can look up from Dan Rather, and I give the reference here, and it shows the use of a portable Raman instrument in Nigeria to detect counterfeit pharmaceuticals, and you may be surprised by, the way pharmaceuticals are stored, distributed, and sold in that particular case. It's quite unlike the US and Western Europe. Typical applications for portable mass spectrometry, the picture at the top is this high pressure mass spec. So it, unlike a traditional lab mass spec, operates at a very high vacuum, maybe 10 to the minus 6 torr. This can operate at a modest vacuum, about 0.1 atmosphere, and so the pumping requirements are much less, which is one of the things that enables it to get into a small form factor. It uses an array of micro ion traps. It's fast. It can be programmed to identify certain target chemicals, and therefore, provides a presumptive method for identification of materials. The bottom picture is an ion mobility spectrometer, and that actually is often made in this dustbuster form factor, but there are smaller versions. There's like a wearable version for the military as well. You may have encountered IMS in an airport. If your luggage has ever been swabbed or your hands have ever been swabbed or anything, they take the swab over to an instrument sitting at the back of the line, put it in it. That instrument's an ion mobility spectrometer. It's a very sensitive instrument to detect trace amounts of materials. And obviously in an airport, they're looking for trace amounts of explosives. Portable X-ray fluorescence, in the picture at the top is a portable XRF. That's been used for at least 20 years in the whole of the metals life cycle. So that starts with mineral prospecting and mining, goes through refining, raw material confirmation when you're fabricating things, in-process inspection, for instance, in petrochemical plants, and onto scrap metal sorting. So the whole of the metals life cycle XRF is used. It's also used for detection of heavy metals such as lead and cadmium in old house paint and imported toys. Used for recycling automotive catalytic converters. Materials such as rhodium are incredibly expensive these days, so catalytic converters are recycled. Even the cash for gold business, some cash for gold businesses will have a portable XRF to assay materials it comes into. They're also used in cultural heritage studies. If you think about it, if you're in the field and you're excavating something or you're looking at frescoes, you can't take those into the lab. And so these portable XRFs are used there. It turns out that for some fairly fundamental physical reasons, portable XRF doesn't work very well for light elements lighter than silicon. And so there's an alternative elemental technique, laser-induced breakdown spectroscopy, or LIBS, which is especially useful there. So it's used extensively in aluminum alloy sorting, as an example, of lithium applications, sort of lithium mining, prospecting. And it's also quite fast for qualitative analysis and things like identification of various ferrous alloys. NMR instruments fall into two broad classes. There's chemical shift NMR, which is typically the one you learn about, and there's what's called time domain or relaxometry. So small benchtop chemical shift NMR instruments are available from a number of vendors, and the picture on the top is one of those. And some of those instruments are capable of advanced pulse sequences and could do more than protein, could do, proton NMR, for instance, could do F19 and NMR. Most of them use the familiar 5mm diameter NMR tubes, but NMR these days can be ruggedized and adapted for sort of process type applications. The middle picture is an example of that. That's an NMR instrument, and it actually uses fairly wide bore plastic tubing, so it's well suited for viscous materials and slurries and applications like that. Relaxometers were developed about the same time as analytical near-infrared instruments, and actually do some of the same kinds of applications like moisture measurements. But again, advances in things like permanent magnet technology and cell phone electronics now enable those to be miniaturized. And the picture at the bottom is a portable NMR relaxometer that's been recently introduced to the market. So we have all these techniques, and we need to understand what technique is we need to use for what kind of analysis. I'm not going to go through this table line by line, but obviously you need to understand: are you trying to analyze molecules, or are you trying to analyze for elements? To start with, you need to understand the phase of the sample. Are you dealing with solids, liquids, gases, vapors, volatiles, semi-volatiles? Are you dealing with pure compounds? Are you dealing with homogeneous mixtures, or are you dealing with heterogeneous mixtures? And heterogeneous mixtures are especially tricky because you have to think about sampling, and you have to think about what area or volume you're sampling. And then you've got to understand the detection limits. Optical spectroscopy is typically only going to give you single-digit % identification limits in condensed phases, and you really need to understand that it's not going to be a trace analysis technique. For trace analysis techniques, you need to go to mass spec type instruments, and with the best detection limits for something like GC mass spec, where you're separating a complex mixture first, and then you're analyzing every peak that comes off the chromatograph. So you need to understand the technique, you need to understand what your target analyte is, what its phase is, and what you're trying to get out of it. But most importantly, you need to understand the detection or the identification limit. So we've talked a bit about, if you like, the engine, the spectrometer itself. And then we've talked about what's needed in terms of environmental ruggedness, of waterproof, dustproof, drop resistant, operating temperature, etc. Those would generate a spectrum or a series of spectra. You then need the application infrastructure to transform those spectra into results for the operator. And so that's a combination of algorithms, libraries, databases, calibrations. And then the final step in the design of what I'm calling here a platform is all the operational considerations, the user interface, the fact that the operator may be using some kind of protective equipment, at least gloves. They may be using it outside where there's a lot of ambient light or glare or sunlight. And you put all those factors together, and you then have a platform. In terms of the analysis, these really fall into two classes, and the goal is to process spectra to give an actionable result to a non-scientist. So for qualitative analysis, in other words, identifications, you're going to be using a spectral database or a spectral library resident on the instrument, along with some kind of matching algorithm that gives a confident result. Quantitative analysis is a lot more difficult. You require a validated calibration there. And so you need a set of calibration samples which have concentration data attached to them. And that data has been generated from a reference chemical method, a standard chemical method. So quantitative analysis tends to be a lot more difficult than qualitative analysis in these instruments. So once we have this platform established for one application, we're up in the sort of top left-hand quadrant here. We then go out into the marketplace and we get exposure and experience. And inevitably, then you get customer requests saying, can you do X? Can you do Y? That really starts a round of new application development, which, as I said, could be accessing appropriate samples, generating a database, generating calibration, picking the right algorithm to use, and any operational considerations. In other words, the sampling and who's going to be using this instrument and where this instrument is going to be used. And that can flow through to generate a new application for an existing instrument. From time to time, new technologies will flow in and give you an enhanced platform, and you can go around this this loop again. And indeed, if you look at the development of portable XRF and portable Raman, that's exactly what has happened. Those instruments were introduced for one particular application. As they got into the market and people used them, they realized they could be used for other applications. Those applications were developed. Meanwhile, the technology was improving and new platforms were developed and new instruments. So you tend to see this sort of circular progression in instrument development. So we talked about the platform, we talked about applications. The third piece to have a successful portable spectroscopy product is an appropriate market channel. So you've got to sell into a market using the right approach, the right language, and personnel. And for instance, I mentioned that XRF instruments are sold into the scrap metal market. So a person that's used to selling, let's say, a high-end mass spec to a professor at a university isn't going to be the right person to sell a handheld XRF to a scrap metal dealer. So in each of those markets, you have to understand the needs of those markets, the vocabulary used in that market, how instruments can be used, what the pain points are, what customers really want, and you have to have the right approach. And it's completely different from selling into a lab, but selling to a scrap metal dealer is completely different from selling to, for instance, a pharmaceutical manufacturing plant on the one hand, or hazardous materials personnel on the other hand. So that's really part one of this, and that sort of wraps up what instruments are out there from that are on the market today. But spectrometers continue to shrink in size. And if you've read Alice in Wonderland, she chases a white rabbit down a hole, looks into a small passage and sees the loveliest garden you ever saw. But she can't go through the passage until she drinks something from this bottle labeled "Drink Me," shrinks in size. And she does indeed shrink in size, but she basically maintains all her faculties. And that's what's happened with spectrometers over the years. They've become smaller with only modest performance reductions, which could be in sampling versatility, spectral range, spectral resolution, and signal to noise. But they've harnessed this ever-increasing power of consumer electronics to be able to generate these reliable, actionable results. So the latest development is the availability of very low-cost multispectral sensors. These aren't full-blown spectrometers. They have a limited number of, if you like, resolution elements with fairly broad resolution, but they're the size of a computer chip. So then that leads to the possibility of embedding them into consumer goods. So the first half of this talk really discussed these completely integrated instruments from major analytical instrument companies, Raman, XRF, etc. And the applications well-defined, controlled by the instrument company. We're now moving on to think about miniature spectrometers, spectroscopic sensors embedded in consumer goods, which is an emerging field in what the trade calls white goods, things like washing machines and refrigerators, and then also in personal care, personal health, personal fitness type products. And here the application is also well defined, but it may just be a single purpose, controlled by the consumer goods manufacturer. Up on the top row, if you're looking to identify hazardous materials, you may have a library of 10,000 compounds. Down on the second row, we're just trying to figure out something fairly simple. So it's a little easier. So this picture is taken from a 2020 review article on handheld near-infrared spectrometers. And in the top left, you can see one of these cordless drill form factor devices, but under it, there's another spectrometer that's literally about an inch cube. And so the near-infrared devices have been shrinking steadily, but it's much more than that. This is taken from a 2021 review article in Science and is talking about the developments in what various people might call photonic devices or plasmonic devices and computational type devices, and looking at the size of them and the footprint. And some of these are very, very tiny indeed. Only a few of these have been commercialized, but it shows you the way the technology is going, that spectrometers, multispectral sensors are getting smaller and smaller and smaller. So I mentioned that multispectral spectrometers may have a very limited number of spectral bands that they use, and they may be broad, and so they're not conventional spectrometers. So the first question that people might have is, can you actually do useful science with these? And in fact, multispectral devices have been used for a long time. And one example is Landsat, the series of Landsat satellites, which goes back as far as 1972. So they recently had their 50th anniversary, and there's a review article that talks about 50 years of science. So there's many generations of Landsat satellites, but fundamentally they are multispectral scanners looking at the Earth. And so what's the science, if you like, behind being able to use low resolution and a limited number of bands? And this really applies to the visible region and the near-infrared region. So if you look at near-infrared spectra, as you go to shorter wavelengths, you lose a lot of detail. You end up with rather broad lumps, especially by the time you get out to, say, 1 micron or 1,000 nanometers. And fundamentally, many bands are very broad in the near-infrared to start with, especially OH groups. And natural products tend to be dominated by OH groups. And if you look at them, they may have a half width of at least 50 nanometers. And if you look at visible spectra of dyes, of pigments, of colored things in general, they're often very, very broad, at least 100 nanometers half width. So if you put that together with the success of the Landsat program, you come to the conclusion that you could get, in many cases, useful information out of a very small multispectral sensor. And you don't need a full-blown spectrometer for some of these very targeted applications. So there are some devices on the market already. So these are multispectral sensors, a small number of discrete detectors or discrete channels, maybe up to 16. Some of them have already been demonstrated for conventional applications like illicit drug detection. There's a reference to a 2022 paper here. But the key point I'm making here is that because they're small size and low cost, because they're pretty much semiconductor devices, potentially they can be incorporated into wearables like smartwatches and smartphones, as well as in other consumer devices. So just looking at these, so A has 14 channels operating in the visible region. B has 16 channels operating in the near infrared between about 850 and 1700 nanometers. C is actually a near infrared array detector. It's a new generation lead salt detector, but you can see how small it is. And then D is another module designed to be incorporated in other devices with 16 near infrared channels between 1200 and 1700 nanometers. So there are these very small multispectral sensors on the market today. So what could we do with them? I mentioned white goods, and this is things like refrigerators, ovens, washers, dryers, and it's sort of optimal operation. There's one example that people have talked about is using let's say you've got a stain on the fabric. You could use a sensor to identify what the fabric is and identify what the stain is, and then automatically program the washing machine for the optimal conditions to take that stain out. You could get spoilage alerts for produce sitting in a refrigerator. And as these devices get smaller and lower cost, they could go into, smaller appliances, kitchen gadgets like toasters, rice cookers, slow cookers, etc. There's been a fair bit of discussion about putting one of these sensors in a robot vacuum cleaner. And here you're quite simply trying to determine what surface the vacuum cleaner is on at any particular time. Is it on carpet? Is it on wood? Is it on tile? Is it on something else? And then you can tweak the operating conditions, adjust the operating conditions on the vacuum cleaner for each of those surfaces. A lot of interest in fitness in smartwatches and sport watches. That there are devices on the market already in the sports watch type category that monitor skin hydration and oxygenation. In the personal care industry, and I've got an example of this I'll show in a moment, it could be what cosmetics to use, how to apply them smartly and automatically, what hair products to use, do I have enough sunscreen on? In personal health, you can have a smart toothbrush. You can spectroscopically tell the difference between enamel and plaque, and you can go beep, which would indicate to the user you need to brush longer here to get rid of that plaque. I'm going to talk about smart toilets a little bit in a moment. Indoor air quality, we have existing smoke detectors and carbon monoxide detectors. Those could be smarter. They could detect methane, so you could detect natural gas leaks, for example. They could detect formaldehyde, which sometimes you get from outgassing from some furniture products. By the way, you won't detect radon by an optical spectroscopic method for obvious reasons, because it's a monatomic, no noble gas. So let's have a look at some of the examples. You may have seen this, the Aura ring. It's actually packed with a whole bunch of different kinds of sensors in here. Originally developed as a sleep monitor, but now it's in its third generation, I think, monitoring even more things. Although not a spectroscopic product, this is kind of cute. You can actually buy a vacuum cleaner that's equipped with a laser and a particle counter. And this, this sounds like Austin Powers. It's got a laser in it. This is a product from Dyson, the vacuum cleaner company. So it's got a green laser that tangentially illuminates the surface, and it shows up all the dust. It's got a particle counter in it that actually gives you a histogram by the particle size of how many particles you've picked up. So it's not a spectroscopic product, but it's certainly a photonic type product that's appearing in regular commercial products. This is only fairly recently on the market, and the New York Times has a columnist that regularly reviews tech products, and so earlier in the year he reviewed this, and he says, as someone who tests lots of cutting-edge gizmos, I wasn't expecting to be blown away. But when I pressed the trigger to activate the vacuum, my mouth gaped open and I began spewing profanities. To my horror, the laser showed that every inch of the floor and every room of the house is blanketed in a light layer of dog fur. So he has a corgi, and corgis are notorious for shedding. He went on to say, once I saw it, I couldn't unsee it. It was like when Neo saw the Matrix, but instead of green lines of code, it was dog fur. Instead of gaining the ability to fly, I had a newfound neurosis about cleanliness. This product is a hair analyzer, and it does incorporate a near-infrared spectrometer and an optical sensor as well. You can see it's formed a bit like a clip, and it basically goes around a person's hair and analyzes the hair and then transmits that information to another device that makes a custom formulated hair product for you. And so this comes from a company called Henkel, which is a German or personal care product company. There's sort of the German equivalent to Procter & Gamble. And it's marketed as a Schwarzkopf Salon Lab. So I mentioned smart toilets, and this is where we potentially get a little gruesome here. Every year there's something called the Consumer Electronics Show in Las Vegas. And then this is taken from a review of this year's show in the Wall Street Journal. And the Japanese company Toto has been talking about making a smart toilet for several years. And they say, the release date, years, not months from now, and the specific technologies is still under wraps. But the concept here is you could have sensors embedded in the toilet seat to measure heartbeat, body fat, etc. And then sensors can detect clues about the user's health, checking urine and stool for abnormalities, etc. All that data then gets uploaded to the cloud, and what comes back is, say, suggestions for diet, suggestions for improving your health, assessing stress levels. And so this article starts by saying, the suggestion pops up on your phone in the produce section of the grocery store. Your diet seems unbalanced. The recommended recipe is salmon, chicken, avocado salad. And that message may have come from your toilet. So is this crazy? Is this science fiction? There is, in fact, a startup company that has something like this on the market today. This they call it a multi-frequency spectrometer. So it uses an array of 64 LEDs, a different frequencies, different wavelengths, in other words, spanning from the high UV to at 350 nanometers to near infrared at 2500 nanometers. It's mounted in the front of the toilet, projects to the back, where there's an array of photodetectors. And again, this is coupled to either your smartwatch or your phone. And one of their slogans is "Urine is the new blood." And so, then, is there really bedrock science behind this? And the answer is yes. You can go into the refereed analytical literature and you can find papers. So here's a 2020 paper, a mountable toilet system for personalized health monitoring via the analysis of excreta. And so the smart toilet automatically sends data. And again, it sends it up to the cloud, and it's a sort of precision health type application. Smart toilet, self-contained, operates autonomously, leveraging pressure and motion sensors, analyzes the user's urine flow rate, volume of urine, using computer vision, classifies stool, etc., etc., etc. So, what are the conclusions here? There are already a number of devices on the market that have spectrometers or spectral sensors incorporated in them. And we're going to see more of them. And smart fingers, smart rings, smart glasses. A lot of people looking at embedding sensors in clothing, smart watches, etc., etc., etc. So I have a caveat here. The holy grail in this area would certainly be non-invasive blood glucose measurements. And people have been working on this literally for 35, 40 years. And it hasn't been really solved yet. And you can actually download a book from the web called The Pursuit of Non-Invasive Glucose, which is now in its 8th edition. And it's written by someone who was there at the beginning and has worked and consulted for a number of companies trying to do this. It turns out it's a very challenging problem. Nonetheless, there are a number of companies that are working on this today. There's one major photonics company called Rockley Photonics that's looking at a photonic integrated circuit type approach, so they could put everything that's needed to do non-invasive blood glucose in a wearable. But also looking at measuring core body temperature, blood pressure, glucose, hydration, etc., etc., etc. So what's the conclusion here? So spectrometers have been shrinking over the years, started with room-filling behemoths to the familiar 2-foot square beige boxes, to being transportable within the lab, to handhelds. And I think that the development of these low-cost, very small multispectral sensors is the latest stage in this. And we're going to see those and other photonic devices embedded in consumer goods, eventually reaching smartphones, smartwatches, other wearables. You'll have spectral sensors in your home, in your pocket, and they may even turn up in very unlikely places. So just a little plug here for further reading. I was one of the editors of these two books that came out just over a year ago. So volume 1 covers the whole of portable spectroscopy and spectrometry technologies and instrumentation. Volume 2 covers applications. So if you need any information on any kind of portable spectrometer, this is the key reference. A version of this presentation is going to be in the November issue of Spectroscopy magazine that will be out fairly soon. And the chapter 23, the last chapter in volume 2 here, I wrote a chapter on the future of portable spectroscopy, which is again a bit of a forerunner of of this talk. So that concludes this talk. I'm happy to answer any questions, and I hope that you A, enjoyed this, and B, sort of got got something out of it, and are intrigued by the possibilities of portable spectroscopy. Thank you.
All right, thank you, Dr. Kirkholm, for your excellent presentations. Let's see if we got any questions from the audience. Oh, yes, we do. I think Dr. Hutter is asking, especially for mid-infrared chemical analysis, where do you think the field of the mid-infrared components, such as spectrometers, lasers, detectors, heading to in the next few years? This is the first. Yeah.
Hang on, let me just. Yeah. In terms of mid-infrared, mid-infrared is sort of a challenging region, spectroscopic region, because traditionally the sources aren't very bright and the detectors are noisy, and therefore you needed big optics to to get nice data out of it. FTIR instruments have been miniaturized down to those handheld formats that I talked about. There's a number of possibilities here. If you don't need the full spectral range that an FTIR gives you, you could use different light sources. So you could use LEDs, you could use mid-infrared lasers, and there's a lot of work being done to in what are called photonic integrated circuits to try to get those components such that they can all be put on a chip. And there is a MEMS-based FTIR out there. It's a little limited in its wavelength range, going into the mid-infrared. There are possibilities. If you look at where a lot of the work is being done right now, obviously there's a lot of work being done in LiDAR, which involves tunable lasers, fast swept source lasers, special detectors like SPAD arrays and things like that. There's a lot of work going on in optical coherence tomography. Some of that could spill over into the mid-infrared. There are lots of possibilities in the mid-infrared for further miniaturization of these devices. The sample interface and interpretation of the data can be a little tricky. Mid-infrared really ideally wants